Good afternoon, ladies and gentlemen. Thank you for coming today. I'd like to quickly introduce myself. I'm Kamal from PJB, a Standard and Design Engineer. I'm looking forward to talking with you today about our paper entitled Computational Simulation of Gas-Solid Flow to Reduce Erosion in a Circulating Fluidized Bed Boiler. This afternoon, I'd like to present our research about the computational particle fluid dynamics simulation in a CFB boiler. I also want to introduce our team. There are Pradita Yusi, Ahmad Barkati, Henry Pariaman, and Muhammad Hisjam. My talk this afternoon is divided into 5 main sections. The first is introduction of the background of our research. The second is the literature review. The third is the material and method that we use in the study. The fourth is the result of research. And finally, or the fifth, is the conclusion. Feel free to ask any question. However, I do ask that you wait until the end of the presentation to us. Let's start with the introduction of our research. As we know, circulating fluidized bed or CFB is one type of cold combustion technologies that plays an essential role in the power generation plant and coal gasification industry. High efficiency of gas-solid separation is a key to achieving high combustion efficiency, reducing limestone consumption and NOx emission to meet the demands for high steam parameters and sizable thermal capacity. A detailed overview of the fluidization characteristic in the large-scale CFB boiler was provided by using CFD. There are two types of theoretical approach that one can use in computational fluid dynamics to describe gas and solid flows. The first is a continuum approach for both phase, which is known as Erosion or two-fluid model or TFM. The second is a continuum approach for the fluid and a discrete approach for particle phase, also known as Erosion-Lagrangian or discrete particle model or DPM. The TFM model treats solid as a continuous phase that interacts with the gas phase through an exchange of momentum. The TFM model has limitations, such as not applicable to distribution of particle size and interparticle force. The DPM model describes a discrete phase by tracking the many particle trajectories that exchange mass, momentum, and energy with the gas phase across the simulation field. The DPM model takes into account the particle size distribution and the interaction between particles. Recently, an Erosion-Lagrangian model called CPFD was used to model gas-solid flow in a fluidized bed. CPFD simulation provides a feasible means to capture the dynamic characteristic of the gas-solid flow within a fluidized bed quickly and accurately. Chen used CPFD to simulate the CFB riser, and Wang et al. Used CPFD to simulate the CFB's gas-solid flow characteristic with a U-type loop cell. Therefore, this paper performed three-dimensional simulation of a CFB using CPFD software. This paper has focused on simulating the gas-solid flow characteristic to predict the erosion area that occurs so that it can be optimized for better CFB boiler reliability. Moving on to the next point, I'd like to present the literature review of our research. In the boiler, there is flow when a substance enters the boiler. Liquid or gas that flow into the boiler in sufficient quantities and will pass through the bed particles will later form a particle suspension. In the end, a flow will be formed. The drag force acting on the particles of the gas flow must be at least in the same range as the gravitational force to obtain fluidization. The lowest speed at which all the particles are suspended by the gas is called the minimum fluidization velocity. If the speed is greater, it will cause different behavior. Is fluidized by a combination of the behavior of the two forces on the particle drag force, FD, which is caused by the flow of fluidizing air and the force of gravity, or FG. FD is linearly dependent on the area of the particle, as explained in equation 1. FG is linearly dependent on the volume of the particle, as explained by equation 2, according to Newton's second law of motion. As the particle size increases, the force of gravity increases more than the drag force increase. Therefore, larger particles tend to survive, while smaller particles are more likely to move along with the gas flow. For CFB, this results in average particle size at the top of the riser being smaller than the average particle size at the bottom. The next is about CPFD mathematical model. The CPFD methodology takes an Eulerian-Lagrangian approach to describe the gas-solid flow in three dimensions. The gas phase is described as a continuous phase with strong coupling to the discrete solid phase in mass and momentum equation. As we can see, this is the detail of CPFD mathematical model. Next is interface drag model. The interface drag function is defined by when you model in reference 29. Next is solid stress model. The present study the particle normal stress model by sorry 1, 2, 1, 2, 3. The next is about interface drag model. The interface drag function is defined by when you model. And the solid stress model, the present study adopts the particle normal stress model by Harris in reference 30, as you can see in this equation. I'll move on to my next point, which is the material and method of our research. The first is computational method and model. The study was carried out by simulating the flow patterns of the particles in the CFB using CPFD software. The 3D CFB model for simulation is based on the geometry and size of the CFB available in technical drawings with 3D CAD software. Then the 3D models are exported in .stl format. The parameters used in the simulation are based on the data drawn from the operational condition of CFB, visible on the DCS control room, and boundary condition of the result of the calculation of cold stoichiometry reactions. Combustion process that involve chemical reactions are ignored, and the combustion chamber temperature is considered isothermal. 3D models of CFB and location of our boundary condition are illustrated in figure beside. And the next is about simulation setup and parameters. The parameters used for the simulation boundary condition are shown in Table 1 and Table 2. The simulation is carried out by assuming isothermal condition, where the temperature value is considered constant at 1070 Kelvin. Gas viscosity and density also affect cross-phase drag values, which in turn have an impact on the velocity profile and particle distribution in simulation. The sand particles used in the simulation have a density of 2200 kg per meter cubic and a molecular weight of around 60 gram per mole. The particle size distribution SD of the sand is represented by the graph in figure 2. This leads me to my next point about the result and discussion of our research. The first is gas-solid flow pattern distribution. The pattern of solid or sand particle flow is shown in figure 3a. From the pattern of particle distribution, it appears that the particle dominate in the refractory region. This shows that the particle is backed down and not circulated through the cyclone. Simulation performed by changing the working parameters of CFB according to the calculation of cold stoichiometric reactions or ideal condition show different particle flow patterns. The number of particles rising to the top decreases significantly. With this condition, erosion occurs only around the refractory wall. There is erosion on the cyclone. This can also be seen from the pattern of air velocity in the decreasing cyclone area. This condition is good, but the effectiveness of heat transfer through particle convection can decrease. And next, the second result of this research is about erosion intensity and location. Erosion caused by the flow of solid can be seen in figure 5 and 6. From the analysis, it can be seen that the greatest erosion occurs in the refractory area. This is due to the particle moving and hitting walls at an angle where erosion is most likely to occur and at a relatively high speed. The speed of particle can reach up to 30 meters per second. The magnitude of the speed of this particle is in line with the air velocity, which is also high. The fluidization rate calculated by dividing the total flue gas volume at the furnace temperature but the top furnace section is usually around 5 meters per second. To avoid erosion, it generally doesn't exceed 6 meters per second. Moving on to the last point, I'd like to present the conclusion of our research. In this paper, CPFD was used to predict the flow characteristic in a practical CFB boiler system, considering the fluidizing air velocity in a large-scale gas-solid system. The pattern of particle distribution that dominates in the refractory region indicates that most of the particles descend into the bed and are not circulated through the cyclone. Erosion occurs a lot in several places, including refractory walls, return legs, and some circulation areas. Decreasing the parameter of working condition, according to the calculation of cold stoichiometric reactions, shows a decrease in erosion, but it can reduce the effectiveness of thermal transfer in the furnace. The simulation only shows the location of erosion. It does not calculate the amount of erosion. Therefore, it is necessary to analyze further the erosion amount occurring. And that brings us to the end. Thank you so much for your interest and attention. If anyone has any question, please feel free to ask now, and I will do my best to answer.